All right. Have we seen factorial notation before? Okay, so the exclamation mark, right? So when I see n followed by an exclamation mark in mathematics, that doesn't mean just shout n. Okay, it's read as n factorial, and it's defined to equal n times n minus 1, so that would be the number that is 1 less than it, times n minus 2, the number that's 2 less than it, all the way down till you get to 1. All right. Now, another way of representing a factorial, you could say n factorial is n times n minus 1 factorial. So as an example, I could say that 10 factorial is the same as 10 times 9 factorial, right? Okay, couple special situations. 0 factorial, that equals 1. 0 factorial equals 1. A lot of people have trouble understanding that. Chances are when you've learned about factorials in the past, you probably learned about it in terms of like combinations and permutations. Maybe back in like your geometry classes, I think is where the standards fit that in. But the results of a factorial, they'll tell you how many different arrangements are possible for a given set, okay? So as an example, if I have 5 factorial, that's 5 times 4 times 3 times 2 times 1, right? Or 120, okay? So this result of 120 means if I have 5 different items and I'm trying to find all of the different possible ways of ordering those, there's 120 different ways. Okay? So going back to 0 factorial equals 1, so think of it this way. If I have nothing, there's only one way of ordering that. No way. Think about that for a second. If I have nothing to order, then there's only one way of ordering it. No way. That means there's technically one possibility. Does that make sense? Okay. Let me give you I found an interesting proof to that as well. So it kind of uses the notation of n factorial being n times n minus 1 factorial. So let's say this. Let's go proof. X factorial can be thought of as x times x minus 1 factorial. Now I'm going to solve that for x minus 1 factorial. Okay, so I'm going to now say that x factorial divided by x is equal to x minus 1 factorial. See what I did there? I took the original and I just divided it by x on both sides. Okay, now let's say I want x minus 1 factorial to turn into 0 factorial. What does x need to be then? It needs to be 1, right? So that would become 1 factorial over 1 equals 1 minus 1 factorial. Well, 1 factorial is 1. There's only one way to arrange one element, divided by 1. So therefore, 0 factorial equals 1. There's your proof. Okay. All right, back to the other example here. 12 factorial divided by 10 factorial. I can say that this is equivalent to 12 times 11 times 10 factorial. I'm going to stop there, given that we're dividing by 10 factorial. And those can reduce away now. What's 12 times 11? 132. Okay. Keep these factorials in your back pocket as we move into the next example. Okay? They're going to show up again. All right, so the other way of defining a sequence is recursively. Okay? When you have a recursive formula, the nth term of that sequence is being defined by previous terms in the sequence. Okay? So you need to be given at least one term of the sequence in order to find other terms. Okay? All right, so let's focus on the recursively defined sequence to the left here. It says find the first 5 terms of this sequence. So we are told that S sub 1 is 1. The first term of the sequence is already known to be 1. Okay? Then our recursive formula says S sub n, the nth term, is equal to the value of n itself times S sub n minus 1. So here's where notation is important. When I say S sub n minus 1, this is the term before S sub n. Okay? All right, so let's find S sub 2. That means n is 2. And then we would be multiplying that by S sub 2 minus 1, which is 2 times S sub 1. And we already know S sub 1's value to be 1. So 2 times 1 is 2. S sub 3, n is 3, multiplied by S sub 3 minus 1, or that's 3 times S sub 2. And we just found S sub 2 to be 2. 3 times 2 is 6. All right, so see what we're doing here? We're simply taking the number n and we're multiplying it by the previous term of the sequence. S sub 4 would be 4 times S sub 4 minus 1, or 4 times S sub 3. That's 4 times 6, or 24. And then S sub 5, n is 5 times S sub 5 minus 1, or that's 5 times S sub 4, which is 5 times 24, or 120. All right, do we recognize what's going on here? S sub 5 resulted in 120. Go back, look at 5 factorial. 5 factorial is equal to 120 as well. So that means this recursively defined sequence explicitly can be defined as S sub n equals n factorial. Okay. That's just an interesting situation that the factorial can be represented with a recursively defined sequence. All right, next one, I have us define recursively using function notation. So I'm saying f of 1 equals 3. The first term of the sequence is 3. And then f of n plus 1 is equal to 3 times f of n minus 2. All right, so the notation is switched here a little bit, not just with function notation, but also we now have n plus 1 and then n. So that means f of n is the term before f of n plus 1. Okay?
Okay, and let me know if there's anything else I can help you with.
All right. So f of 1 we're told is 3. So then f of 2, that really means n is 1 here. Okay? If n plus 1 is supposed to be 2, then n is 1. So this is going to equal 3 times f of 1 subtracted by 2. We just found f of 1, or we were told f of 1, I should say, is 3. So this is 3 times 3 minus 2, which is going to be 7. F of 3, that means n is now 2. So this equals 3 times f of 2 subtracted by 2, or 3 times 7 subtracted by 2, which is 19. F of 4 means n is 3. So this equals 3 times f of 3 subtracted by 2. That's 3 times 19 subtracted by 2, or 55. And lastly, f of 5, that means n is 4. So this equals 3 times f of 4 subtracted by 2. That's 3 times 55 minus 2. What do we get there? 3 times 55, that would be 165 minus 2, so 163, right? All right, one more example. This is a special one. Okay, once again, give me the first 5 terms of the recursively defined sequence. Here we are given the first 2 terms of the sequence. A sub 1 and a sub 2 are both said to be 1. And the reason we're given 2 terms is because the formula is defining any given term by the 2 preceding terms. A sub n plus 2 equals a sub n plus a sub n plus 1. Those are the 2 terms that directly precede a sub n plus 2. All right, so if I want a sub 3, that means n is technically 1 here, right? 3 is equal to n plus 2. That means n is 1. So this equals a sub 1 plus a sub 2, which is 1 plus 1 or 2. A sub 4, that would mean n is 2, is equivalent to a sub 2 plus a sub 3, or 1 plus 2, which is 3. And then a sub 5 would mean n is 3. This would equal a sub 3 plus a sub 4, or 2 plus 3, which is 5. All right, so let's list those out as a set. 1, 1, 2, 3, 5. What would be next? 8. After that, 13. After 13, 21. Okay, you get the idea. You're just adding the 2 terms that precede it, right? All right, so notice we're calling this the Fibonacci sequence. Okay, probably the most famous sequence out there. The terms of this sequence are known as Fibonacci numbers. Okay, if you do a quick Google search, you're going to see that the Fibonacci sequence leads you to the golden ratio and the golden spiral. Okay, and these are concepts that come up often in nature, honestly. Okay, let's just pull one up here. Okay, so You go to the Fibonacci sequence, mathisfun.com. Fibonacci sequence is the series of numbers. Now they throw a 0 at the beginning. Sometimes you see a 0, other times you don't. So the sequence is listed there. And now notice it says when we make squares with those widths, we get a nice spiral. Okay, no, this is known as the golden spiral. Okay, so if you zoom in, you have these two squares in the middle there, both with a width of 1 next to it, so square whose width is 2, and so forth. And we just have this nice spiral pattern associated with it. And these squares fit neatly together to form that spiral, and that spiral shows up in a lot of natural applications. Okay. Now you don't really see it drawn very well in this flower, but let me pull up a better image. Okay, and you can kind of see that the makeup of this flower, you have this spiral pattern to it. Okay, and that's just one of many natural applications to this. I also found that there's a lot of graphic design principle where the golden spiral is utilized as well. Okay. All right. So if you're intrigued by that, maybe research it a little bit more. Okay.